So in this video I'm going to review some useful functions, right, which I probably should have called them elementary functions or basic functions or whatever, the kinds of functions you encountered in high school. And since we're just covering the basics, I'm going to go for the basics. I'm going to talk a little bit about linear functions, about power functions, about exponential functions, and logarithmic functions, as they go together. And I'm also going to talk a little bit at the end about trig functions, or trigonometric functions, because they do come in handy every once in a while. So linear functions are the simplest of functions, right? It's just a straight line. There's my function. Of course, I should start off. I'm going to call my axes x and y. And actually, I'm going to do that over. So first things first is always going to label my axes. They're going to be x and y this time. So linear functions are the simplest of functions. A linear function is just a straight line. And we know that the equation of a linear function usually is of the form y is equal to mx plus b, where m is the slope, which is how much the function increases in y for every change in x. And b over here is the y-intercept, which is over here, and it just tells you where your line crosses the y-axis. The slope and the intercept tell you everything you need to know about a linear function, and if you need to change something about your linear function, if you're tailoring it to fit some data, those are the only two things about it you can change. If you increase the slope, then you get a line that's steeper. If you change the intercept, let's say I want the same line but with the intercept up here, then you're going to get a parallel line but with a different value for b. And that's really all there is to it. And when you're modeling, you're going to use linear functions if you know that there's some proportional relationship between your variables that's constant over time. Where linear functions assume that y increases as some steady multiple of x. In a power function, we assume that y increases as x raised to some power. So the general form of a power function being y is equal to ax to the power of b plus c, where a is still kind of slope, c is going to be some hint at your intercept, because when x is equal to 0, c is what's left over, and b determines the rate at which the slope changes as x increases. So for a basic power function, I'm going to start with y is equal to x squared, which is the canonical parabola. Y is equal to x squared. And we know intuitively that if you increase the exponent, then the function's going to go off towards infinity faster. This is, the red line is y is equal to x cubed, which means the point where they cross is 1, 1, because 1 squared is 1 and 1 cubed is 1. So x to the anything always goes through 1, 1. And if I increase the exponent a little bit more and I go for y is equal to x to the fourth, that's going to go off to infinity even faster. Going to go through the same point. And it's always going to be positive. Even powers are always positive. Odd powers can have negative values. And you notice that these lines stack in the opposite direction when x is less than 1. That's just because if x is a fraction, right? If x is a half, x squared is a quarter, x cubed is an eighth, x fourth is 1 over 16th. So these x to the fourth gets small really fast as you get less than 1. So going back to our basic equation of the power function over here, if we change a, that'll change the value of x by a steady multiple. So let's say if I wanted y is equal to 2x squared, that's going to be just a little bit steeper than y is equal to x squared, because at every point along the curve, the value of y is going to be double what it was. Similarly, you can say multiply by something small, and that'll flatten it out a bit, because at every point y is 20% of what it was originally. If you want to move your functions around, then you manipulate c, because simply, right, if y is x squared plus 2, then that changes my intercept, because when x is 0, y is equal to 2, so I'm going to start off here and have exactly the same function for y is x squared as I had before. This is starting to get a little messy, so I'm going to erase some of these lines. But there we go. Another potentially useful form of power function is when the exponent is itself a fraction. So let's try y is equal x to the half, which is the same as the square root of x. Well, you know, all that's also going to go through 1, and then just slowly get bigger forever. This square root function can be good for processes that don't asymptote, but slow down in the rate at which they increase over time. And finally, you can flip any one of these functions upside down by making an equation of the form y is equal to c minus ax to the b. So instead of starting at 0, your function would start at c and be a mirror image of its former self. So one last thing I should mention. We've talked about how to change the slope of your function at any point and have to shift it up and down, but since we've moved beyond straight lines, you can also shift a power function right or left. So in order to, let's shift y is equal to the square root of x a little bit around. Then we add, let's call it d now. So if I want to shift my function to the left or right, I add something to the value of x at any point. So if let's say I add 1 to x at every point, that's going to give me y is equal to x plus 1 to the 1/2 is equal to the square root of x plus 1. So when x is 0, you're actually going to get the square root of 1, which is 1. When x is -1, we get the square root of 0, so we'll go through 0. Which means I've just taken my square root of x function and shifted it to the left by 1. So then this always mixes me up to this day. If I want to shift my function to the left, I add something to x. If I want to shift it to the right, I subtract something from x. And before I go, I should just draw in for completeness that y is equal to x squared should be, or y is equal to the square root of x, sorry, should be symmetric into the negative part, because if x is 1, the square root of 1 is positive 1 or negative 1, because negative 1 squared is still 1, negative 2 squared is 4, right, so y can be positive or negative. So that should be all of the main intuitions you need to remember about power functions. I'm going to talk about exponential functions a little bit more at length because they come up so often in population biology in particular, especially as regards population growth. So I think of exponential functions as like a sort of special case of power functions where, as you recall from moments ago, right, as you recall from moments ago, a power function has the form y is equal to x raised to some power. In an exponential function, you end up with y being some base raised to the power x. Or, in a more general form, some constant times some base raised to some exponent times x. That's not right either. The general form of an exponential function should be something like y is equal to some constant times a base raised to some rate exponent x plus some constant for a y-intercept shift. But for starters, we're going to go with the simplest case, where most of those things are equal to 1, and your exponential function is just your base raised to the power of x. The most common bases used in exponential functions tend to be 10, 2, and e, which is approximately equal to 2.172, but is actually an irrational number that goes on forever. And I'll talk more about that later. But for now, just go with it. It's e. And all these fundamental exponential functions have a thing in common, is that they go through when x is 0, the function has y equal to 1, because anything raised to the exponent 0 is 1. So let's look at some of these. Let's say y is equal to 2 to the x. Then if y is So just do a quick over here, little table of values. When x is 0, 2 to 0 is 1. When x is 1, y is 2. When x is 2, y is 4. When x is 1/2, y is the square root of 2. When x is -1, y is 1/2, etc., etc., etc. So we go through plotting those. 0, 1, 1, 2, 2, 4. So most exponential functions tend to look like this, where as x goes off in the negative direction, the function will asymptote towards 0, but it can never be 0. And as x goes off in the positive direction, y goes off towards positive infinity. If we do the same thing with a different base, y is equal to 10 to the x. At x is equal to 0, we still go through y is equal to 1, but when x is equal to 1, now 10 to the 1 is 10, and this function is going to go off to infinity faster, and it's going to asymptote down towards 0 faster. And since y is equal to e to the x, e is in between 10 and 2, it's quite close to 2 actually. E to the x is going to look quite similar to 2. And just like with any other function, if you want to tweak an exponential function, you can shift this intercept upwards by adding something at the end. You can change the steepness with which the exponential curve goes off to infinity and back towards the asymptote by adding a multiplier to x, or by adding a multiplier to the whole thing. And if we want to shift our function to the left or the right, then we mess with x. If I add something to x, that'll shift the function over to the left, just like I did with our power functions. And if I make it x minus 1, that's going to shift me over to the right by 1. And the last important thing about manipulating exponential functions is to remember what happens when the exponent becomes negative. When x is positive, we think of exponential functions as being exponential growth. On the flip side, quite literally, if we try and plot e to the negative x, we find at x is equal to 0, we still get y is equal to 1, so we still go through the same intercept. But all the other points are flipped around the y-axis. So as x becomes large and positive in the function, it becomes the same as when it's large and negative, and y asymptotes down towards 0 without ever getting there. And as x becomes more negative, y goes off towards infinity. So just remember that exponential decay functions are mirror images of their corresponding exponential growth functions. Logarithmic functions are closely related to exponential functions, and by closely related, I mean they are the inverse of exponential functions. So by inverse, I mean if we define y to be equal to e to the x, then it's necessarily true that x is the logarithm with base e of y. And correspondingly, if we say y is equal to log base a of x, that means x is equal to a raised to the power y. That is effectively the definition of a logarithm. Quite often in mathematics textbooks and in general usage, people will drop saying what the base is. Half the time, they're assuming you know that it's base 10. And the other half of the time, they're assuming you know they're using base e. Sometimes also people will use log of x to mean log base 10, and they'll use ln of x to be log base e, because ln is the natural logarithm. Since e is a natural number, it's a whole other story. But as I mentioned before, exponential functions and logarithmic functions are inverses. So there's a really easy way to get the plot of any log function out of its exponential function. So I'm going to replot y is equal to e to the x. So we remember it goes through 0, 1, goes off to infinity, and asymptotes down towards 0, like that. Since the log is its inverse, y is equal to log base e of x. The inverse of any function is a mirror reflection across the 45 degrees y is equal to x line. So instead of going through 0, 1, the logarithmic function goes through 1, 0. So the log of x, log base e of x, goes off to infinity very, very slowly, and asymptotes down towards y is equal So instead of going through 0, 1, the log goes through 1, 0. As x becomes large and positive, the logarithm also goes off towards infinity. As x approaches 0, y goes towards negative infinity. And it's important to note, x can never get to 0. And in fact, the logarithm, if you try on a calculator to take the log of a negative number, it's undefined. And if we look at our other common exponential function, y is equal to 10 to the x, which, as we recall, gets bigger faster and asymptotes down faster. By the same token, the log base 10 of x gets bigger more slowly and asymptotes towards the y-axis more quickly as x becomes small. Manipulating a logarithmic function works the same way as manipulating any other kind of function, log base e of x. If I want to shift it up or down, I can add or subtract a constant. if I want to change the slope at every point, I can add a multiplier, and if I want to shift left or right, I can change x to be x plus or minus some number. Trigonometric functions, or trig functions, are a little bit different because while we've still got a y, what's usually the x-axis is actually defined as being theta. So I'm going to go back to the very beginning. You'll probably remember learning trig functions as having something to do with right triangles, but for me, I think of them as having to do with the unit circle. So this is my circle with a radius of 1. It's not the best circle, but just trust me, it's a circle. So for any radius, any unit vector in here, we automatically create an angle between my vector and the x-axis. And that angle is theta, which creates a right angle triangle. With respect to theta, this is the opposite side, this is the adjacent side, and this is always the hypotenuse. So as theta goes from 0, so if this was my unit vector, then theta is equal to 0, and as it goes around the unit circle up here, this one, theta is equal to pi over 2, this one, theta is equal to pi, theta is equal to 3 pi over 2, and back to the beginning where theta is equal to 2 pi, which is the same triangle as when it's equal to 0, which is why trigonometric functions all cycle back on themselves. So those trig functions are y is equal to the sine theta, which is equal to, with respect to any theta, the opposite over the hypotenuse. Cosine of theta is always the adjacent over the hypotenuse, and the tangent of theta is opposite over the adjacent, or sine over cos. I don't really need to say much about trig functions beyond this, and to remind you how they look. I'm just going to put a 1 and a negative 1 down here, and label pi and 2 pi. Those are radians, by the way, I'm sure you remember. So first we're going to plot y is equal to sine of theta. When we start at 0, the opposite is 0, and the hypotenuse is 1. So sine always starts at 0, 0. When we get to pi over 2, our opposite is going to be all the way the same as our hypotenuse. It's going to be 1. We get back to pi, the opposite is 0 again. When we get to pi is equal to 3 pi over 2, our opposite is 1 again, and at 2 pi we're back at 0. So the sine function goes up to 1, back through 0, down to negative 1, over a full cycle. And cosine looks almost exactly the same, just shifted a bit. If we go back over here and assume at theta is equal to 0, this time adjacent is 1 and hypotenuse is 1, so cosine starts up here at 1. At pi over 2, the adjacent is 0. Go through 0. Over here at pi, we're going to be negative 1. 3 pi over 2, we hit 0 again, and then back to 2 pi at 1. So cosine starts at 1, goes down. I had a teacher who used to always tell me that it was snaky sine and a cup of cos, for what it's worth. And we're going to plot tangent, even though you will rarely use it for anything in the life sciences, because at 0, our opposite is 0, so tangent is 0. But at pi over 2, opposite is 1, but adjacent will be 0, and 1 over 0 is undefined. So tangent actually has an infinite asymptote as it goes off towards pi is equal, as it goes off towards pi over 2. Then it starts again at negative infinity, comes up towards 0, and then asymptotes up again, and then comes back and goes through 0. Now the most intuitively useful function, but there it is. Just like with other functions, if you want to manipulate a trig function, sine or cos usually, let's go start with y equals sine theta. If I want to shift my function, then I add something to theta. So I can manipulate that to be sine of theta plus or minus some amount to shift to the left and to the right. I can add a multiplier to the beginning so that, so for example, y is equal to 2 sine theta. Instead of going from 0 to 1, it'll go from 0 to 2, and it'll just change the amplitude of the waves. And if I want to change the frequency of my function, I can add a multiplier to theta. So y is equal to sine 2 theta will cycle twice as quickly. So it'll go like that. I think I probably did that too many cycles, but you get the point. And for a function that cycles like this, mostly what you're going to want to change is the amplitude of the cycles and their frequency. If you want to get fancy, there are other kinds of transformations you can do to trig functions, but most of the time for modeling in biology, changing the amplitude and the frequency will get you where you need to go. At first it might seem odd that I'm going over trig functions in a mathematical methods for life sciences class, but really there are plenty of things in biological systems that have cycles. Hormones have daily cycles, weekly cycles, monthly cycles, and a lot of organisms have seasonal cycles. So when you're modeling systems like that, trig functions, particularly sine because it starts at the origin, can come in quite handy.